Hello everyone and welcome back to another calculus video. In this video we are going to talk about the shell method. The shell method is another way to find the volume of a solid of revolution. So if you remember in the last video we talked about the disk method where we took a volume, a solid of revolution. Let's say this is my f of x and I'm rotating about the x-axis. So I'm creating something that's going to kind of look like a vase here. And I cut everything into discs. So I sliced it this way and I drew a representative line here. A lot of textbooks will talk about a representative rectangle so you can see that slice, but this slice was always going to be perpendicular to the axis of revolution, even if we had something that we were rotating about the y-axis. So let's say we rotated this piece about the y-axis. So it would create something that looks like this open area in here. When we slice perpendicular to the axis of revolution. So all my representative lines or rectangles would look like that. And that creates those discs that we were looking at finding the volume of. With the shell method, I want you to think about a shell. You know, when you go to the grocery store and you buy some kind of canned item, maybe you buy some canned green beans and it's got this label on it. If you were to pull that label off, that label would be a rectangle, but we can form it into a circular shape if we wanted to put it back on the can. Think about those labels as your shells. That's what they're looking like. So we're taking our figure, whatever it is. So I'm going to look at this figure here. I'm rotating it about an axis to create this three-dimensional object that I want to find the volume of, and I'm filling it with an infinite number of these labels. And I got to figure out what's the volume of each of those labels, of each of those shells. So if I want to find the volume, I've got to figure out what the volume is for each shell, and I'm going to add them up, and that's where the integration is going to come in. So the volume of this is really just a rectangle, but this distance here would correlate to the distance around the can. So that's the circumference of the can, which would be 2 pi times the radius. And then we would need the height. So that would find the area here of that rectangle. And if I multiply that by the thickness, then that would give me the volume of that label that went on that can or that shell. And if I were to do that an infinite number of times with an infinite number of labels that are going to have different heights, then I could find that volume using integration. So the radius is going to be referred to as P of X or P of Y, depending on if we have a horizontal or a vertical axis of revolution. And this is always going to be the distance from the axis of revolution. And like I said before, the important thing about the shell method is that our representative rectangles are going to be parallel to the axis of revolution. So if we have a vertical axis of revolution, like if we're revolving about the y-axis, we're thinking about everything in terms of x. So that distance from the axis of revolution to a representative rectangle, and it's going to be a variable distance. That's important to note. So this is going to be in terms of x, and then we have a height that's going to be variable also. That's going to depend in this picture on whatever that function is. If we have a horizontal axis of revolution, the distance from the representative rectangle to the axis of revolution is going to be our POY. So we're thinking about that as a vertical distance instead of a horizontal distance. That's why we're thinking about things in terms of Y instead of in terms of X. And then we've got the height that we're going to think about in terms of Y. So let's look at a few examples. I really want to focus on setting these up. The integration for these will be fairly simple. We might integrate one, but I'm going to focus on the setup here. Let's say we want to find the volume of the solid of revolution formed by revolving the region bounded by y equals x minus x cubed in the x-axis. And we're bounding this between 0 and 1. And we're going to go about the y-axis. So this is a vertical axis of revolution. So when I think about setting this up, I'm thinking about setting things up in terms of x. So my volume, is going to be 2 pi. We're integrating from a to b. This is p of x, h of x, dx, where dx is representing our thickness of each of the shells here. So if I were to graph y equals x minus x cubed, so here's my function. And I'm going to recreate this on my graph down here. And we're bounded by the x-axis, and x is between 0 and 1. So we're really just worried about this piece that we're rotating about the y-axis. So if we were to revolve that about this axis, I'm going to erase this extra piece here. Do you see what it's going to look like? It's going to look kind of like a bundt cake, if you will. It's going to be something like this, with this crevice on the inside. And like I said, it's going to look kind of like a pound cake that's cooked in a bundt shell or something like that. So how would we find the volume? We're bounded between 0 and 1. P of x is the distance to the axis of revolution. So in this case, my distance would be x. My height is going to depend on the function, which is x minus x cubed dx. So if we wanted to integrate this, we're going to have x squared minus x to the 4th dx. So this is going to be x cubed over 3 minus x to the 5th over 5. And we're going to evaluate from 0 to 1. So we're going to have 1/3 minus 1/5 times 2 pi. So this is going to be 2 pi times 2 over 15, which is going to be 4 pi over 15. So that would be the volume of that figure, of that bundt cake, if you will. So let's do a what if scenario. What if we took that same figure, but we rotated about x equals 2? How would that change what's going on? Let's just look at the setup here. So my volume is still going to be that same formula. It's going to be 2 pi. I'm still bounded between 0 and 1 because I'm using those bounds in the x-axis. I'm just changing the axis of revolution in this case. So we need the distance to the axis of revolution. And then we need the height. Well, the height of the figure is not going to change. It's still bounded by x minus x to the third. We just have to figure out the distance. So I'm going to draw a new picture here to show this scenario. So here's the piece of the graph that I'm concerned about. This is at x equals 1. I want to look at rotating about x equals 2. I'm rotating here. I got to figure out what my distance is to the axis of revolution. So from here to here, my distance is 2, but my representative rectangles, now I'll draw a representative rectangle up here also. My representative rectangles, that's what I need to find the distance. What's the distance from here to here? Well, as I fill in this figure, as I move across, that distance is changing. The maximum it's going to be is 2. And then x here represents the distance from here to here. So if I want this distance, it would be 2 minus x. Okay, well, what if we change the scenario again? What if we rotate about x equals negative 2? How does that change what my setup looks like? And that's what I'm really concerned about. So everything is going to remain the same except that p of x value. So again, I'm going to draw my picture. So this is at 1. If I rotate about x equals negative 2, I'm rotating here. Here's my representative rectangle inside the region. I know this distance is x. I know this distance is always 2. And remember, we're talking about distance. So that p of x would be 2 plus x. So you can see how p of x changes depending on where we set that axis of revolution. Let's look at another example. Let's say we want to find the volume of the solid revolution formed by revolving x equals e to the negative y squared. And we're going to bound by the x-axis, and y is going to be restricted between 0 and 1. Now we're going about the x-axis, which is a horizontal axis. So if we're looking at a horizontal axis, we're integrating things in terms of y. I'll write our formula down here. I'll call these C and D. So you can see my figure here. And I'm going to recreate this in a rough drawing. I want to revolve this about the So here's my rough picture of that. Looks something like this. I'm revolving about that x-axis there. Here's my bound. I'm bounded between 0 and y equals 1. So here's y equals 1. Here's my region that I'm revolving. So when I revolve that, my representative rectangle, it's going to be like this. Remember, it's going to be parallel to the axis of revolution. So let's figure out what my volume is going to be. We know we're bounded between 0 and 1. We're thinking about things in terms of y now. I need to figure out what my distance to the axis of revolution is and what my height is, and then integrate with respect to y. So my distance to the axis of revolution is going to be this guy, and that's going to be y. My height of this is going to be in terms of that function e to the negative y squared. So that's what we would end up integrating. So we're going to have 2 pi integrating from 0 to 1. I'm going to rewrite this times y dy. We're going to think about a u substitution. So u would be negative y squared. So I need a negative 2, compensate with a negative 1/2. And then when I integrate e to the u, I'm going to get e to the u. I'm going to evaluate from 0 to 1. When I plug in 1, I get e to the negative 1. When I plug in 0, I get e to the 0, which is 1. So this is going to be 1 over e minus 1. And then I'm going to distribute that negative in, which is going to change the signs here. So my final answer, I'm going to write as 1 minus e times pi. So it's not a nice answer, but that is the answer to that one. Let's look at another example. Say we want to find the volume of the solid formed by revolving the region bounded by the graphs y equals x squared plus 1, y equals 0, x equals 0, and x equals 1 about the y-axis. So let's draw a picture. This is a quadratic shifted up 1 unit. So here's my quadratic shifted up 1. I'm bounded by y equals 0, x equals 0, and x equals 1. So here's x equals 1. I'm really looking at just this region in here. We want to revolve about the y-axis. So we are going to set up both of these. I'm going to show you shell first, and then I'll show you what disk would look like. So I revolve about that axis and creating this three-dimensional figure that's going to look something like this. I think we created something similar for another problem. This is a vertical axis of revolution, so we're thinking about things in terms of x. In this case, we would integrate from 0 to 1. That's the bounds of the region. The distance to the axis of revolution is x. That's talking about this distance here. The height of the figure, so the height of that representative rectangle is going to change along that quadratic. That's going to be x squared plus 1 dx. So there's my setup for shell. Just for fun, let's set up disk so that we can compare. So if we were to set up disk method for that same figure, I'm going to redraw that figure over here. There's x equals 1. There's my region. I'm revolving this way. So I have to slice perpendicular to the axis of revolution. So you can see how my disks are going to change. Down here, my disk is going to be always a radius of 1, but up here, after I pass where that vertex is really, my radius is going to vary some. And we're thinking about that thickness in terms of y, so we're integrating in terms of y. So let's set this up. This is going to be set up as two different intervals. We're going to go from 0 to 1. I'm going to do this one first. That radius is always 1. So it's going to be pi times the integral of the radius squared times dy plus pi times the integral. Now we're going to go from 1 to this point here. If x equals 1, and this is the function y equals x squared plus 1, then that y value is going to be 2. So we're going to go from y equals 1 to y equals 2. And then we just have to figure out how we're going to create that hole. So this is going to be your washer method. So the distance from here to here is that distance of 1. So that's the outer radius. The inner radius is going to be defined by this distance in here. And to find that inner radius, we're going to have to take our function and solve it for y. So if I were to solve this for y, I would subtract 1, and then I would take the square root. Since this is bounded in the first quadrant, this has to be a positive square root. So there's my inner radius. So both of those intervals will give you the same result. The question is, which one would you want to use? And in this case, we can see that the shell method would be easier for us to integrate than the disk method. Both will yield the same results though. And in a lot of cases, you'll be able to set these up either way. There are cases where you may only be able to set up and evaluate one way. Pontoon is being made in the shape of figuring pontoon is designed to be rotated that about the x-axis. So let's look at another example. A pontoon is to be made in the shape below. Kind of looks like um, a kayak, really. The pontoon is designed by rotating the graph of y equals 1 minus x squared over 16, and x is bounded between -4 and 4. We're going to revolve that about the x-axis, where x and y are measured in feet. We want to find the volume of the pontoon. So if we were to graph that figure, 1 minus x squared over 16, it's going to be a quadratic. That's going to be upside down. And we're centering this at 0, 0. I'm sorry, we're centering this about the y-axis. So I'm bounding from -4 to 4. So in this graph, you can see the symmetry here. And we could graph it in Desmos and get the exact same thing. We're going to set this up with shell and disk, so you can see the two and compare. So let's say we set this up with shell. So if I set this up with shell, I would want all of my shells to be parallel to the axis of revolution. So my shells would actually run this way, because this is my axis of revolution. And since my axis of revolution is horizontal, I'm thinking about distances in terms of y. Thinking about things in terms of y is a mind shift from what we typically think about when we think about things in terms of x. So we're going to have to think about, what are these bounds here and here? So you can see this guy's crossing the y-axis at 1. So we're bounded between 0 and 1 for y. The distance to that representative rectangle, that p of y, is going to be y. We just got to figure out what h of y is going to be. So what is the height of this thing? So let's do some fancy math off to the side. If we have the function y equals 1 minus x squared over 16, and we want to solve it for x, we're going to, I would multiply everything by 16 to clear the fraction. I'm going to move the x squared over here and the 16y on the left, and then 16y is going to go on the right. I'm going to factor a 16 out, and then I'm going to take the square root. So when I take the square root, I'm going to get plus and minus here. This would be 16 times 1 minus y. And square root of 16 is 4, so I could pull that out. So 4 square root of 1 minus y. And that is plus and minus. So x equals plus and minus. So what that means is this positive piece on the right hand side in quadrant 1 is represented by 4 square root 1 minus y. This piece over here is represented by the negative of that because that's the negative x values that's coming out. So if I want this side and this side to be accounted for, I could think about it in a couple of ways. I could think about symmetry here, or I could think about area under the curve going back to Calc 1. So it would be right side minus left side. So 4 square root 1 minus y minus negative 4 square root 1 minus y times dy. And that's the same thing as 8 square root of 1 minus y times dy. So there's my setup for that. And you see that integrating that's going to be a little bit more complicated. That's actually going to involve integrating using by parts. Let's set up disk, which is the way that they set the picture up for us. The reason that we know that that's disk is because that representative rectangle is perpendicular to the axis of revolution. So with disk method, it's pi integrating from our bounds. In this case, our bounds are negative 4 to 4, and it's going to be that radius squared. Notice we do not have a hole in this. So this is disk method, not washer method. So what is the radius of that rectangle? Well, it's based on that curve, which is going to be 1 minus x squared over 16. So if it were me trying to figure out area here, or volume here, I would want to use the disk method because that method is going to be easier for us to integrate. We could just multiply everything out, and then we could integrate and we could find that final answer.